start recording. All right, so I'm recording now. Let me go over here. Okay, so let me go over here, and I'm going to open up the calendar. And I'm going to share this. So we're actually doing really well on time. I like where we are. You can see here, we've completed singular value decomposition and recommender systems. Today, we're going to wrap up singular value decomposition and dimensionality reduction. So this will basically wrap up this topic, okay? And then, as I said, on Wednesday, March 3rd, it'll just be a catch-up lab where we look at all the homework assignments that have been due or that are going to be due, and to answer any questions. Next week, I'll do reinforcement learning, which is, I'm sure you guys are going to be pretty interested in that, given that 10 years from now, according to Elon Musk, we're all going to be we're not going to drive anymore, apparently. So cars will drive themselves and all that. So anyway, whether that's true or not, we will definitely take a look at reinforcement learning. I'll give you guys, and I will do an example called taxi cab. Which is basically, it's a 2D, so not so like an Atari type, right? So if you guys ever played Atari, it was only 2D, right? No 3D component. But we'll take a look at how a game could be played. So it's going to be mostly games, obviously driving a car, driving a plane, or flying a plane, I should say, or simulating a nuclear power plant and whatever happens inside the reactor, right? All those things could, in theory, be modeled with reinforcement learning. So we'll take a look at that. And then we'll have the spring break. And then after that, we have the rest of the semester to cover. We'll have a good 4 weeks to cover the very important sequence of neural networks, okay? So I'll start with the perceptron, have to give you some foundations on how do the algorithms work for perceptron. I'll start, give you all of that. Everything that goes together. Interestingly enough, linear regression, logistic regression, all of those are very similar to neural nets. So all of it will be discussed, and then we'll wrap up the semester with hidden Markov models and k-means, which are k-means is like KNN. It's almost like KNN, so it's very straightforward. Hidden Markov models might be a little bit new, but it's also, I think in one day we can pretty much cover it. All right, so that will be, and then also at this point in the semester, we need to start talking about projects, okay? So given that you guys, are a very small class, I would suggest that you form groups of 2, okay? So form groups of 2, maybe one group would be a group of 3, unless somebody just wants to go and be a group of 1, but I would encourage you to work with a partner, okay? We'll talk about the project also on Wednesday, so that you guys can give me, you've had now enough, right? I've given you enough of topics. I've given you a lot of supervised learning. I've given you now recommender systems, and I'm gonna give you next week reinforcement learning, okay? If you think what comes after spring break, it's another type of classifier, just like KNN and naive Bayes. So the things that we're gonna discuss there are do the same thing as KNN and naive Bayes. So even though it's very important that we discuss them from the point of view of what they are and how they work, just because, they don't do anything new, okay? You already know how to classify data. So just like you would take iris or MNIST with naive Bayes and KNN, you would take iris and MNIST with these algorithms of neural networks, and it would pretty much be the same result. Obviously, neural networks, though, are the game changer in AI, but if you guys have an interest in this course in data science, you can certainly take our graduate level courses, 520 and 530, which go into applied machine learning, which is TensorFlow and getting into the algorithms for big data, and then of course, just a course on deep learning, all the different algorithms. That's really, if you go into industry and work in the field, you know, you need to know deep learning, but we have a course, an entire course for that, but it's good that you've taken this one because this is the foundations, okay? And in particular for deep learning, these 4 weeks will be essential, okay? Because I won't use TensorFlow. I'm not gonna, you know, as you've seen, all I'm using is NumPy. And, you know, I'm trying to keep it, you know, every now and then I use sklearn, sure. But I'm trying to keep it just NumPy so that everything is as close to being written from scratch as possible, okay? Anyway, so that's the plan. So I haven't updated the calendar yet. Reinforcement should be down here. Open lab or catch-up lab on Wednesday. I do need all of you to come to class though, because, you know, like I said, I'm gonna ask you questions about your homework, etc. And then today then, so that's basically the announcements. Do you guys have any questions about anything that I just said before we get started with today's lecture?
No questions.
All right, great. All right, so so now today is March 1st, so that's great. Today we are just going to wrap up singular value decomposition. I went over these two topics, you know, last week, the topic, right, as it relates to recommender systems. Remember that singular value decomposition is let me actually switch over to the whiteboard, although we're going to use our Jupyter today, but let me switch to this. All right, so as you remember, I told you guys last week, that singular value decomposition is a technique, SVD, right? Now we can go, you know, there's a lot of, if you guys have an interest in the math of this, and I actually strongly recommend that you take a look at it. There's a great book that I recommend. You know, read this on your own, okay? This is a great book. So, you know, you usually take a course called linear algebra. You can take all these other courses, but really there's a nice book out there that is just for machine learning. It's called actually Linear Algebra and Optimization for Machine Learning. And it is written by, it just came out like last year. So you guys, this is a gem, a treasure, honestly. And it hasn't been around before. So think of how lucky you guys are that you actually get to read this book. It's by somebody named Sharu. He works at IBM. C. Agarwal. Okay. So if you have, it's a very accessible book. It doesn't require, you know, background. Linear algebra is actually a course that you take. You need basically like algebra. Some people want you to take calculus for it, but for machine learning, that's not required. You see, that's my whole point, is that some people will say, no, take all the calculus and then take linear algebra and whatever. Yeah, but that's if you're going to be a mechanical engineer. Right? But for machine learning, you don't need all of it. You only need certain areas to understand them really well. And basically what we've been doing with NumPy, right? So the little tricks that what I've been doing with NumPy comes from that. And if you're curious, it's, you know, you just have to buy the one book, and it's actually only half of it is linear algebra. The other half is optimization, which is actually the topic that after spring break, I will start covering. Now, keep in mind, I only cover intuitions, right? If you've noticed, I hardly ever cover any of the math. My interest is not to, you know, bore you with that, or because as you can see, at the end of the day, we just did, what was it, numpy.linearalgebra.svd, and that was it. So there's no need for us to understand the algorithm at such a low level. However, for those of you that are curious, it's definitely an excellent read. You know, next week, usually the way that I like it is I just like to teach NumPy, and, you know, like we did at some point in the semester, right? And hopefully you've continued going over that, that link. I just haven't had time, honestly, to fit so much material. Now, I should say ITS 265 that is being offered next semester by Professor Tae-Hoon Kim will be much more, whereas I'm focused on algorithms like singular value decomposition using NumPy, he will just, this is NumPy, you know. And so he would cover matplotlib, he'll cover pandas. You've seen me use pandas, but he's gonna formally, that's what 265 is actually for. It will also teach you the intro to AI stuff, like, you know, how historically with chess and everything, how, you know, Claude Shannon did the first games, you know, that, so it should be a very fascinating class. I strongly recommend, if you have the time, to take 265. In theory, you would have taken 265 before 365, but, you know, since we just started this concentration, we're kind of adapting it as we go to the students. But anyway, I do recommend this book for sure. If you like a good read, certainly, you know, don't think of it as a book that you'll read over 2 years, right? So, you know, take every chapter slowly and just, it'll definitely be very valuable, especially if you have an interest in this area, which, you know, as you might imagine, will just continue to grow. Now, that being said, so I've not really gone into the math. I kind of thought about it, and I was going to do, but I've decided, you know, it's not really necessary. And in particular, I gave you that example last week, right? So I gave you, I think, that good example on recommender systems. We looked at the data. Take a look at it again. Today, I'll do the same. I'm just going to use NumPy. As you know, this time around, so I said singular value decomposition is a technique from linear algebra that has been around for, you know, centuries, very powerful. And it's used at least for two things: recommender systems, which I basically covered last week. Today, I'm just going to wrap it up, and then also compression. And compression is today's topic, okay? So compression, so this one already covered, and then this one I'm gonna cover today, and that way we will wrap up singular value decomposition, the topic. Keep in mind, you know, we're using NumPy right now. NumPy is highly efficient, but when you're talking about big data, right? Big data, you're gonna be talking about, you know, millions of records. So at that point, singular value decomposition is a little bit intensive when it comes to memory. So, however, even though we are using the NumPy implementation, be aware that for big data, there's going to be TensorFlow, PyTorch, and what have you, implementations for GPU, etc. Additionally, there's another one for compression. So now let's move on to just the topic of compression. Okay, so compression. So first, I'm going to motivate what I mean by this, right? And then once I've motivated what I mean by compression, then we'll just go back to our Jupyter notebook. I also have, there was one part of the code last week that because I was going so fast, I couldn't get through. So I want to get through that as well today. But we should be able to do it and wrap up the course. So compression, basically, first of all, there's some techniques out there, right? The most classic techniques are singular value decomposition and another one called PCA. Right, so PCA, they both have some underlying background and they have some similarities. I just happen to like singular value decomposition because I think it's a lot more intuitive. And in particular, if you start with recommender systems, I can do better examples of it. And so that is much more helpful. But as you saw me, I did recommender systems last week. this week we're going to do compression of the data. And so first of all, I'm going to need to motivate why compression is important. We're not, unfortunately, we're not going to be able to cover PCA this semester, but just keep in mind, if you understand how singular value decomposition works, you understand how PCA works. Just like, you know, you do NumPy dot linear algebra dot SVD and SVD, and then something, right, the data, you might imagine it's pretty much the same thing, lin algebra PCA. So that's really, and then they give you very, very much similar results, and then you can just use those results, okay? So that's the idea, you know, as far as, you know, we can take it. But let's just think a little bit, first of all, about, let's think, there's one thing I wanted to say about singular value decomposition. Okay, there's one thing I wanted to say, and that is, you know, I could have, we're not going to derive, obviously, you know, singular value decomposition. Unfortunately, there is some, singular value decomposition is a very elegant technique. So it actually, I think, and you can actually go through it, and you can go through it and derive the singular value decomposition math and algorithm very intuitively, very elegantly. But I just thought, you know, maybe it's not necessary. So really what I will say is this. Imagine that you start the derivation of what singular value decomposition, all of it. As it turns out, once you get to the end of it, you get basically to a conclusion, all right? Singular value decomposition has a conclusion, and basically it's called a theorem, okay? So there is a theorem. So long story short, if you will, I'm just going to say there is a theorem, okay? A theorem for singular value decomposition. And the theorem basically says the following. And that's really, and this is what's beautiful, because PCA has a theorem as well, but it has like these conditions, if you will. And what I like about singular value decomposition, there's no real conditions to it. So let's just go over what the theorem says, and we'll go from there. So it basically says every matrix, and you know what a matrix is, right? So a two-dimensional array, that's what a matrix is. So every matrix that is A, you know, called A, that is M by N, so that is, this is A, and it's M by N. Look at that, that's it. That's the only, you know, characteristic there, has a singular value decomposition. That's a singular value decomposition. Okay? And what that basically it means is that a matrix can be broken up into three matrices, okay? So we basically can say that, so now we can conclude, given a matrix that looks like this, so I'm gonna say, you know, that's the original matrix, right? And I'm gonna call it A, and it's gonna be M, and just to give it more intuition, because this is helpful, think of it as users, right? Users, for the recommender system. That, you know, that's so helpful. Remember, as I was saying also, when Netflix came up with the Netflix prize, they actually, you know, the best solution was based on somebody that took singular value decomposition, and obviously they did some optimizations to the algorithm, but it was a singular value decomposition based solution, the best one that, you know, Netflix has. Okay, so we're saying that a, you know, m by n, where this, let's say this would be the items such as the movies, but it could be whatever else you guys, you know, for your homework, right? Whatever you're gonna be selling, you know, shoes, you know, food, whatever. And so this one is going to be equal to several matrices, right? So it's gonna be equal. So this is, and this is all, this always holds, right? So this is going to be m by r. Some people use the letter K, it doesn't really matter. And this is the matrix U. And then it's a multiplication of these matrices, right? And then the next matrix is gonna be of size R. And we'll talk about this R. What is this little R? And this is, I think we were calling it in the code, we call it S, okay? And then finally, we have this one like this, right? Where this is N, the items, okay? And this is R here as well, okay? So that's an important thing. So this little R is called a rank, but more importantly, you know, we can think of it as what it is. So we start with an m by n rating matrix, A, of m users by n items, and we decompose it into the product of 3 matrices, which are these, okay? And that's, you know, guys, so that is a theorem, okay? So what that means is that that holds all the time, okay? Now, as the algorithm, this little thing has an algorithm in the background that has an optimization goal, right? And it's going to follow the logic, right? But it always arrives at this, right? So if you remember, you get, you know, you get U, S, and V, right? So you get those three pieces of information out. So this one is V, okay? And so that's the idea. So U is an M by R matrix. S is a square matrix R by R, right? That just means that, you know, dimensions are equal. And V is an R by N matrix, R by N matrix. R is called the rank of the rating matrix. Okay, and really what happens in S is really a diagonal matrix, okay? So that's really one important thing, is that basically there's only values on the diagonal and everything else is a 0. And this is important because these values have meaning, all right? These values have meaning, and it corresponds to the concepts here. So the R, so that's why you can see its link, right? So this little R, you can see is here, 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 right? So the R's are correlated to these new columns. Remember that this is M by N. You know, this was, let's say, users, this was the movies, and these are the values. These new this is still the users, okay? So this is still the users. But this is no longer the movies, right? Remember, we already talked about this last week. This is actually the concepts. So latent, sometimes they call these the latent components, or the components, or the principal components, or the singular components, whatever you want to call it. They're those concepts that we talked about last week, okay? But the key thing is this R, because this R indicates the importance of them, okay? It indicates the importance of them. And what I mean by that is the following. So let's say that, so this is really important, right? So let's say that we have the matrix M by N, and we apply singular value decomposition, and now we get M by R, and this is R, you know, multiplication, R by R, and then this is R by N. So what happens is, here you have values, like let's say I'm gonna make up some values, 10, 3, 7, 0, 0. Do you see that? What this implies is the, oh, sorry, they should be in order, so that's my mistake. So let's say at 100, and then this is 20, and then 7, right? And everything else is 0. What does that mean? Well, the principal components are also, let's call them P, I guess, P1, P2. because these were F1, F2, F3, right? All the way to Fn, but these are no longer the Fs. These are now P. So P1, P2, P3, P4, dot, dot, dot. And then here we have the same thing. These are another set of principal components on this side, but they're also in order, P1, P2, P3. And these are still F1, F2, F3. So these are still the movies, right? So these are still the movies, but now we've created these principal components. So they're in order. And the order of the values here correlates to the order of the values here. So what that means is the first principal component is the most important because it has a value of 100. All right, given that it has a value of 100, this would be 100. So this is the most important. The next most important is the one that has a value of 20. So this one. So this one is also important. This one, 7, a little less important, but let's say it's still important. However, the next one is 0. You see that? So what you do there is you can basically disregard those principal components, and you just end up with P1, P2, P3. So think about it. You had a matrix. You had a matrix that was M by N. After singular value decomposition, you have a matrix that is M by R. However, by looking at these, you can actually discard some of them, and you actually can then end up with a matrix that is a matrix that is now smaller, M by K, let's say. So where these are principal 1, principal 2, principal 3, you had, let's say you had here F10, right? And now you have P3. So initially, if you think about it, you went from a matrix that was, let's say, M by 10, now to a matrix that is M by 3. Do you see that, guys? It is basically like you transform the features F1, F2, all the way to F10, dot, 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 into P1, P2, dot, 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 P3, basically. So there's only 3. Does this concept make sense, guys?
Yeah.
And that's called compression. So if you remember, before, when we were looking at Weka, we did ranking, right? So we looked at the features, we ranked them, and then we just picked a few and dropped the other ones. But the difference was it was still the same features. They hadn't been transformed. This time around, they have been transformed. P1, P2 are no longer the Matrix or, Casablanca or Star Wars. They are now, remember, as we talked about this with the recommender system, they are now action movies, comedies, Will Ferrell, right? So whatever the concept is that it discovered, they're new. They're new transformations based on the combinations of data. And so this is the application of singular value decomposition. Let's think about it. Let's think of 2 applications of it. Let's say that I have a data set that is, now I'm going to use some numbers. So I have a data set that is 100 by 20, okay? All right, I have some data there. First thing, 2 questions. Let's say that, or actually just 1 question here. Can I visualize this data? So we know that these are the samples, right? So before, in recommender system, these are always users, but it doesn't just have to be users, right? It can be any data. So let's go back to MNIST, right? So let's say that in MNIST, actually, so if it's MNIST, this is 784, right? So these are the samples 1, 2, all the way to S100. So they're images, right? Every row is an image. Every row is an image, right? And the columns are just the pixels in a 28 by 28 image. Like that. So every sample is 1 image that has been stretched. 28 by 28 is 784. And then every row is an image, a sample. Now, first question, can I can you visualize a vector that is of size 784? What did we say about every feature? F1, F2, F3. We're saying that is an axis, right? So F1, F2, F3. Unfortunately, humans can't view beyond 3 dimensions, correct? You guys remember that?
Yeah.
So what if you want, now, what if you did want to visualize those images? What could you do? For whatever reason, you say, I want to view, because it's not these pictures, right? It's something else. And I want to view them. Well, one thing I can do is I can compress the data. So I'm going to compress this. I'm going to compress this matrix. Let's call it, X. And I'm going to compress it into, from S1, S2, all the images all the way to 100, right? But now I have to compress it to either 3 or 2, right? So that's usually, so you can compress it to 3. You see? How do we compress it to 3? We're going to take the original F1, 2, 3, 784. We're going to run this through singular value decomposition, okay? And then singular value, so we want this to be, so this is still 784 of the original one, but we run it through singular value decomposition. The algorithm tells us that it's going to give us these 3 matrices. So it's going to be 100 now by R. This is R by R. And then this is R by M, right? So this is still going to be, so if I use the real numbers, this is still going to be 784. So this means also that I can take the movies, right? And for some reason, take the first 3 principal components. However, that's not what I want to do here, right? I don't, I just want I want R to be 3 because I'm going to plot in an R3 space, right? So that means I can get rid of this, and now I'll be able to plot my data. But I need to compress it. If I just drop some features, I'm not going to do such a good job as if I compress it. Now, you don't always get great things to view, but I'm just saying this, this would be accurate. You would be looking at it. So what's going to happen is now, initially, this R might be, I don't know, let's say 600. So it'll be a 600 because we'll talk about this, but singular value decomposition tries to figure out a good number, a suggestion, and says, well, if you keep these 600 vectors, then that's all you need, all right? So that's all you need, basically, and so, something like that. So the idea then is that you would have now, instead of 784, you created 600 vectors. However, you still can't plot that, right? You still can't plot that. You can only plot the first 3. So 1, 2, and end up then with a matrix kind of like this. It's got 100 samples, every image, but now every image has been compressed to only 3 axes, which you can now plot in a 3D space. So this you can view. You guys see that? And that's a good way to, and that's basically compression. You've actually succeeded in viewing your data by using singular value decomposition and only selecting these 3 first columns, okay? So you've selected those 3 first columns. Questions? No questions? Making sense? Now, you might have a couple of questions, right? So you might have a couple of questions. You might say, okay, I know that you want 3 to visualize. However, the algorithm suggested 600. So what does that mean that the algorithm suggested 600, you want to visualize just 3? Well, what that means is the following, basically. If the algorithm suggests 600, that means that roughly, if you just have these 600, you maintain 99% of the information that you had before the compression. So you lost a little bit, but you maintain a lot of it. However, if you only use 3, obviously you would expect this to be lower, right? So this is going to be lower than 99%. So that's, you know, a possibility. So how do you figure out what that value is? You know, if I just keep 3, what exactly is that value for me? Okay, you might ask yourself. Well, as it turns out, there's a way to tell that. And that's called the energy. That's called, you know, usually referred to as the energy. So how does that work? So let's imagine that we have, let's say that we have, you know, an X, right? And it was, let's say, M by N. And then it produced a U, which is M by K, right? And then times a S, we're using S. Oh, sorry, I was using R. R by R. And then here, let me just, so then we're going to say, so, and then finally, we have V, and V is, what is R by M, N, okay? So we can focus on just S, right? And we want to figure out how many principal components we need to select, right? So if we want to visualize 2 or 3, obviously, but then we want to know how much energy is that of the original data, right? Or you might say, well, you know, I calculated the amount of energy of just those 2, 3. Okay, for visualization, that was fine. But for my actual machine learning algorithm, I need more energy than just 3, right? So how do you determine that? So that's what we're going to take a look at now with an example. So I'm going to look at an example here, and I'm just going to say, imagine that I have the S matrix, right? So I'm only looking at the diagonal matrix now, and I'm going to give it some data. So I'm going to say the values are 13.74, 10.88, 1.36, I'm going to have to do this, and 1. Okay, so that's my S. The rest is just going to be zeros, okay? 0, 0, 0, 0, 0, 0. That's why it's called a diagonal. The S matrix, where this one is U and then this one is V, right? But I want to determine the amount of energy. So what you can do is, the energy is calculated, so you can calculate the energy by doing the following. You can say, and it's pretty easy math, you can just take the square of the value. So you can say 13.74 square plus 10.88 square plus 1.36 square plus 1 square, right? Plus 1 square. So you've got that in the denominator. That's all the values. And then you just pick, well, I want to use, if I look at these values, right? If I look at these values, I would probably say, you know, these are pretty big and these are tiny. So I'm going to drop those 2. So that means that if I drop those 2, I end up with 13.74 square plus 10.88 square. All right, so now I need to do this calculation. So I'm going to take out my calculator here, and I'm going to say, well, you guys maybe can help me out. So this is going to be squared. Oops. 13.74 square. That's like 188. And then the other one is 10.88. square plus 118. So here's 188 plus 118 plus 1.36 square. That's only like, let's say 2. You see it's pretty insignificant already. 1 by, 1 square also, right? It's just 1. So now this gives us, if we add the two top values, 188 plus 118, that's 306, right? And below it's going to be plus 3, so 309. And so we take the, the divided 306 divided by 309. Oops. 306 divided by 309. Oh, there, look, 99 or something. So definitely look at how much information we still retain with just these two, and we can just drop the other ones. Okay, so what that means is that if we go back to the data, right, if we go back to the data here, now I'm going to have to do an example here. We'll do this in the code also, but let's say we have our X matrix, which is going to be, 5, 5, 0, 0, 1, and then 4, 5, 1, 1, 0, and then 5, 4, 1, 1, 0, and then 0, 0, 5, 5, and finally 1, 1, 4, 4, 4. All right, so that is our data originally. X. We are going to then get vectors U, right? And here we know this is, the S that I just drew before, and then this is going to be V. So I only care about this. So remember, these are actually no longer users. They're just my data, so they're images, right? So I have like sample 1, sample 2, sample 3, sample 4, sample 5. I really just need 2 components. So I don't need 5. So really, it's going to be minus 0. So these are still S1, S2, S3, S4, S5. And it's going to be minus 27, minus 0.29, minus 0.29, minus 0.45, minus 0.56, and so on, right? So the transformation is, and then let me just do 3 here, 0.55, 0.47, 0.47, minus 0.29, minus 0.18, and one more, which is going to be 0, minus 0.71, 0, 0, 0. You can see something like that. So what this is telling me, the previous one, is just by keeping 2, the first principal components, because they're already ranked in order, and by looking at the energy, which is still 99%, right? So the information is still there. Then all I have to do is pick that one, and I can discard that one. Or, there wouldn't just be 3, but discard all the ones that are there. I don't need them. Just 2 is enough. So basically, my data set that was originally like this now effectively becomes S1, S2, S3, S4, S5, like this, right? And it becomes just these principal components, 1 and 2. Minus 0.27, minus 0.29, minus 0.29, minus 0.45, minus 0.56, minus 0.18, minus 0.29, 0.47, 0.47, 0.55. So all of my machine learning I can do not on this one, right? I'm not going to do it on that one, which is, this one is 5 by 5.
but I can just do it on this one, which is 5 by 2.
You see that? That's compression. I compress the data effectively by using not principal component analysis, singular value decomposition. And I know from our previous calculation of my equation before that I retained 99% of the data. Look at what a great, so you have a lot of confidence that your algorithm can work really well. Does this make sense, guys?
Yeah, this makes sense.
Excellent. Now keep in mind, this can also be used in supervised learning, right? So what did we learn when we were doing KNN and naive Bayes? The only difference was in KNN and naive Bayes was that we also had the labels, right? The labels were there. So this was an image of a cat, cat, dog, dog, cat. Well, that's the same as here, right? So we would have here, in this X, right, would have the labels. Dog, dog, cat. The labels are not used. The Y vector, right, is not used in singular value decomposition. All we have to do is take the X data, transform it, so from here to here. And if you notice, the S1, S2, S3, S4, S5 are still aligned, right? So they're still in their correct places. That hasn't changed. Therefore, the labels are still good. And therefore, now we can do machine learning with only 2 dimensions, a 5 by 2 instead of a 5 by 5. You see that? And this is important. So when might you use this? Let's imagine that you have a data set on your computer, right? You have a data set on your computer. Now you're going to run on your laptop. I might give you a homework like this or something, and it's 100,000 by 10,000 features. Imagine that's a really big data set, right? And then you're going to have a Y that is also 100,000 by 10,000 features, right? So that's pretty big. And so you might say, you might run it because you don't want to do the work, of singular value decomposition. So you run it on your computer and boom, you get a RAM error, right? So the computer runs and it says, not enough RAM, not enough. What do you do then? You're in trouble, right? So here, this is where techniques like PCA or singular value decomposition, you should always, consider both, right, can come in and help you, because what they will do is they will compress the data, right? So now you might compress your data and you end up with 10,000 or 100,000, samples, still the same number, but now now you pick a K, some K, and then the labels are still the same ones, right? This is just 1. So you end up with some size that is much smaller. So where K is a lot smaller than M, right? Where this is, or sorry, N, this is usually M. So then this would be N. You see that? And that's really the trick, that K is a lot smaller. Again, how do you decide what it's going to be? It might turn out that N is maybe 600 or 700, let's say. But that's a decision that you can only tell by doing this, the energy. So you'll have to do the energy calculation and figure out what it is. And that's it. There's nothing else. As far as the intuition of singular value decomposition, that's pretty much how it works, right? You can use it, as I said, for visualization, but in visualization, you're limited to 2 or 3. You got to figure out what that energy is. It'll probably be a lot lower. Or you can use it when you have not enough RAM, right? So you don't have enough RAM. So you run just the X on singular value decomposition. Based on the energy equation, you figure out how many principal components to keep. And then that's it. Then, once you've done that, you end up with a much smaller data set. And now it'll run on your algorithm. And I would say as long as you have like 80% of your energy, that should be enough, hopefully. I mean, at the end of the day, you want to have as much as possible, but it also needs to run. And that's compression. If you notice, it's almost the same thing as the recommender system, right? So very intuitive there. So any questions, guys?
So the energy is basically the amount of data that is retained.
So let me put it in, not data, information. Data would be all of it, because remember, data is just all the data, but data is made up. So let me, actually, it's a very good question. Let's define a few terms that were defined by, by Shannon, Claude Shannon, who's the father of information theory. So data is equal to information plus what? Noise. Do you see that? So really, when the energy represents the amount of information that remains, where it got rid of noise, basically. Now, the other thing that's happening in the information is that, in the data, is the following. So let's say this is users, right? Users, right? And going back to the recommender. Matrix, no, actually even better. Thor, Matrix, some comedy. What's another Thor movie? Thor 1, Thor 2, comedy other one, Thor 3. What's the issue with the Thor movies? They're all Thor, right? Do you guys see that?
Yeah.
Okay, so they're all Thor, which means that if you like one Thor movie and you're a fan, you probably like all three. That's not always true, but right? Sort of. And so what's the issue with these three Thor movies then? They're correlated. Do you see that? It's very likely that you gave it a 5 and you gave this one a 4 and then you gave it a 5, but you kind of like them. So if the data does this, I should say, if your data is that, and they're basically Thor movies, they're correlated. So my point is, once you see this one, the value of these two is not really that relevant. You only need to see one, or maybe let's say even better, if somebody likes 2 of the Thor movies, chances are they'll like the third one. You see that? And so there's a correlation in the features. So these 3 Thor movies can really just be one principal component, Thor. Do you see that, guys?
Yeah.
So that's what's happening, is that if we go back to this idea, the energy is looking at all those correlations, right? Correlated features, and it's getting rid of them, right? It's getting rid of them. It's also getting rid of noise. So really the energy represents the amount of actual useful information that remains. Do you see that? Did I answer your question, Ryan?
Yeah, I would say so.
Any other questions, guys? No questions? All right, good. So that's basically all of compression. So hopefully that makes sense. So what I'm going to do now is we're going to switch to the Jupyter Notebook, and we're just going to do some examples of this. I am going to save this as a PDF so I can load it up under Brightspace, and I don't forget. So take a look at the equation, etc. Because you will, you might be using this for your homework assignment. So let me just. Okay, so now. So now let's switch over to Jupyter Notebook. And we're just going to work through some examples. I'm not going to use the recommender data anymore. I'm just going to use some standard data. So let's start a new one. Share my screen. Okay, so this is the Jupyter Notebook. Let me just change the name. And I'm going to call it Singular Valley Decomposition Compression, because a lot of these are just compression. So we're going to do import NumPy SNP, as you know. Okay. So now let's take a look at what we were talking about. So let's do. So let's just do some examples here. All right, so. All right, so I'll basically work out the example that I had on the board, right? So I'm going to work out that example. All right, so I'm going to call this X. So you should be seeing my, let me see. You should be seeing the bright space environment. Or sorry, no, the Jupyter. All right, so X. Okay. I'm going to create a NumPy array. Right, so a NumPy array, and it's going to be made up of, you know, all the rows. Oops. This should be square bracket. No, it's parentheses. So then there's got to be a square bracket here. And the last one, like that. Okay, so, and then here, let's also give it a data type. So the data type will be data type equal np dot, another example, float 32. Let me also move this parentheses up. Like that. Perfect. All right, so now I have my data there. Or my matrix. Now let's just add the data. So it's going to be 5. Oops, not there. 5, comma 5, comma 0, comma 0, comma 1. Right, those were the numbers that I was writing. Then here, this one's going to be 4, comma 5, comma 1, 1, comma 1, 0. All right, there we go. Then we can add another one. Okay, and this one's going to be 5, comma 4, comma 1, comma 1, 0. Okay, and then we're going to do, that's 3, so let's do 6, 0, so we have enough data 0, comma 4, comma 4, 4. And then this one will be 0, comma 0. Yeah, 0, comma 0. 5, comma 5, 5. All right, and then finally, the last one will be this one. We're going to say 1, comma 1, comma 4, comma 4, comma 4. All right, so there's our data. So we can print it just to see what it looks like. Print X, right? Oops, X. Now, if I had my labels, I would have a vector of 1, 2, 3, 4, 5, 6 labels, right? The Y vector. But we don't need that for singular value decomposition. However, if we wanted to compress a data set for supervised learning, we could always do that. So now I'm going to save this and run it. Okay. I think I made that a curly bracket. Okay. And again, there it is. So you guys see the data? So now we have our array, and now we can, compute basically. It's exactly the same code we had before last week, except I'm not going to normalize it or anything like that here. But think about it. I'm just going to do, singular value decomposition. So that's going to be USV, right? So I have my matrices there, and I'm going to say np dot lin algebra dot singular value decomposition. That's pretty much all I have to do. And I'm going to plug in my my data, right? So I'm going to plug in X. Okay. And then once I have the output, I want to print out the results. Okay. So I'm going to see if I can try print. N U equal, and it's going to be the U matrix. And then I'm going to do, this N is just a new line character, so it's like an enter. And then I'm going to say, maybe a couple of enters. S, I use an uppercase S. And obviously I print out S. And then I'm going to do a couple more. V. And I print out V. So, last week, because we were using the real data set, it was much harder to see, whereas here, because this is smaller, hopefully it'll be a little bit easier to visualize. So I'm going to click on that. And now if I run this, there it is, right? So I have my matrices U, S, and V. Okay, so I have my data there. So now, I have my U, S, and V. And I got the values here. So this is, these are the results basically. So you can see there's 1, 2, 3, 4,
5, 6, right? So the original 6, and then there's 1, 2, 3, 4, 5, 6 actually that it has set, but we can now pick just the more important principal components based on the energy. And we have the V over here, but for this example, we are only really concerned with the U, right? Because that's really our data. So our data is, images of size 5, okay? So we can go ahead then and given the results, let's see. Now we can also try other parameters with singular value decomposition, such as, let's see, this one I haven't tried, but let's try full matrices equal false. So there's a few parameters that you can explore here. Okay, and I'm going to run this. So that's the, so now if I try this true. So actually that one's not doing anything, okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5 values, right? 1, 2, 3, 4, 5. So let's try the other one. False. One, 2, 3. No, they both have 5. So basically now, what we can do is we can take the principal components from the U matrix, right? And that's going to become our new X. So what I need to do now is, let's say that I wanted to visualize it, right? So I want to be able to plot it. So what do? I just pick the first 3, right? So how do I do that? Let's say new X, and new X will be U, right? And now I'm going to do slicing. If you remember, we looked at this at the beginning of the semester. So how do I slice just the first 3 columns from U? What do you guys think?
Wouldn't it just be a 3 after the comma?
But we need to tell it all the rows, right? The
Oh.
rows are still the same. So 1, 2, 3, 4, 5, 6. There's 1, 2, 3, 4, 5, 6, right? Those are the 6 samples. So we still need all of them, right? So what was the symbol for all? You guys remember?
Not off the top of my head, no.
Is it just a colon?
Colon, exactly.
Oh.
Exactly, just a colon. So what about for the, I need to slice, just currently, I'm not thinking about energy, I just want to plot it, so I need the first 2 or 3, right? So let's say that I want the first 3 columns. So how do I slice that?
So would it be like colon 3?
Colon 3.
Okay.
We'll see. We'll see if it's 2 or 3, right? So now I'm just gonna, oops, sorry. Now I can just go ahead and print new X, right? And so I'm gonna clear the kernel here. And now I'm gonna run it. And there's my new X. See that? So I now had this one originally, right? This was my original matrix, which was 6 by 5. Oh, sorry. Yeah, 6 by 5. I have compressed it into a matrix that is now 6 by 3. Make sense? And that's,
So,
go ahead.
So I just have a question. So what this did was essentially scale all the numbers between -1 and 1?
This is a scaled data, yeah. So remember that singular value, the function itself does all the work for you. It does all the heavy lifting. So these values are no longer the values that you see there, correct? It's now going to be these values over here.
And those values just represent the importance of the original value.
Yes, if you want to think, all right, so if you're talking about in terms of just this principal component, right? Remember, that maybe might be science fiction. So it's indicating in terms of science fiction, maybe these three are more science, the last three might be more science fiction because they're the higher numbers.
Okay.
You see that? But that's more of the intuition in terms of recommender systems, right? In terms of what we're doing right now, we're just compressing. You see what I'm saying?
Yeah, I was just trying to make sure I understood what was happening.
Yeah, but remember, there's recommender and then there's this, right? So here, yeah. What's important though is that this first component, the first one, is more important than the last one. That's true. Okay?
Okay.
Because singular value decomposition basically sorts them. When it gives you the outputs of the columns, it's going to sort them. And so you just pick whichever columns that you want, right? So if you can only pick one column, you pick the first one. Obviously, though, you could pick more than that. But here in this example, we picked 3 because we could visualize something that is of 3 dimensions. You know, remember, these are all just points, right? So the first row is just a point in a space of 3 axes. And then the second row, again, is just a point in a space of 3 axes. So we're able then to plot this there and do K and N. Does that make sense?
Yeah.
Any other questions, guys? All right, so that's basically the idea, right? That's basically the idea with recommender systems. We did the calculation, and we have now a way of compressing our data, right? So we have a way of compressing our data. Now the next part might be to calculate the amount of energy that we have, right? And that's given based on this. That's why it's so convenient that it doesn't give you a diagonal. So if you remember in the whiteboard, I pretty much said, you know, it gives you something like this, right? This is the S matrix of the energy, and it's kind of a diagonal. But singular value decomposition, you know, doesn't give you the matrix. It actually only gives you a vector, and that's just to make your life a lot easier, right? Because it's just a vector. So what do we need to do? We would need to take the square of all of these and kind of divide it, right? And it kind of makes sense to square it because the values might be kind of tiny, etc. So we need to square these, right? And then add them up, right? Do a sum, and then just so you know, slice out. So let's try and do that. All right. So let me do clear here. So now, according to that equation, we just want to take a look at the energy. So let's say, you know, so calculate calc energy, okay, from S, right? So S is going to be our new target. So we have to think, first of all, we have to get the square root of a vector, right? So we have to find how to square a vector with NumPy. So let's take a look at that. Okay, so it should be as simple as NP squared. So I'm going to take S square and it's going to be equal to NP dot square, because that's what we were doing, right? We were squaring all the values. Right, so it's going to be this. And then we just plug in S. Okay, so let's print that one. Print S square. Okay. So this is the new vector, correct? So we printed this, yeah. So this is the new vector squared, okay? From the original one. So now, according to the equation, if we want to get the energy, how would we do it? We can try energy equal, and you know, we're just going to divide, right? So it's going to be S squared because that's all of them. So we got that one already, right? And then now we want to figure out the different energies. So we're going to do energy S squared. And what would you suggest?
Couldn't you just splice it?
Exactly, slice it, right? Not splice it. So slice it, but very good. Let's just slice it, right? Perfect. So in this case, we're just going to say, because this is a vector, it only has one dimension from beginning to whatever. So let's start with, let's just see, there's 1, 2, there's 0, 1, 2, 0, 1, or there's 1, 2, 3, 4, 5, right? So let's say to 5. All right, and we're going to print the energy. Let's see what it gives us. It's not defined. Did I not change them? Oh, I made the same mistake twice. Okay, so it did it by, okay, so yeah, I'm missing one thing here. NP dot sum. NP dot sum. Okay. That just sums all the values in the vector. And the answer is 1, right? So the answer is 1. So far, so good. So now let's take 4. So we're going to drop 1. Okay. Repeat the process. Run it. Still 1. Okay. Do 3. .99. Do you see that, guys? Here? Do you see that?
Yeah.
Right. So it went down a little, but what does that mean? It means to just we've dropped what? 5 and 4, right? So we've dropped this one, and we've dropped this one. That means we just have 3 principal components. So really, this matrix here, which is 6 by 3, would hold 99.67% of the energy still. That's pretty good. We've managed to reduce dimensionality by 2, and we're still retaining a lot of the information. Now let's just do 2 here. Clear again. 1. Still 99.6 with just 2 principal components. Oh, wait, no, hold on. I think I did that in the wrong place. Yeah, I did this in the wrong place, sorry. I did it for 3. Actually, what I meant to do was here, right? I need to do the energy. So 2, and actually we would view 2 and it would be 2. So we're going to see a matrix of just 2, and we're going to know the energy of just 2. So let's do that. Save it. Run it. 99, it went down just barely, and we have 2 components. So you can see that, and it makes sense. This data, if you look at it, is pretty straightforward, right? That's the thing. There's really a correlation. Like these 2 first columns seem to be very similar, and then these 3 columns need to be very similar. So it makes sense that the first 2 are made into one, and these other 3 were made into another one. Now let's see what happens if I just do 1. So I'm going to go over here. I'm going to do 1. And also I want to see the energy for just 1, the amount of information that is retained. So I'm going to clear, save it, run. What do you guys notice now?
It's only 61%.
Well,
what's your conclusion?
We lose nearly 40% of the data.
By just keeping 1 principal component, right? So if you do if you make X, which was 6 by 5, into a matrix that is 6 by 1, you only retain 60% of the information. That's not great, correct? Guys?
Correct.
Lost a lot. So now I ask you, now that you've seen me do all of this, what would you do? What would be your choice?
You mean like make sure we have at least 2 rows?
I don't know. You tell me. Not 2 rows, columns, right?
Columns, yes. But I have a question.
Just answer my question. Imagine I gave you this exam on the question. I've shown you all this data. What would be your choice of principal component? And why?
It would be 2 columns because we can keep nearly 99% of the data with that.
Okay. All right. So if I do 2, and I do 2 here, okay, and then now I do this here. Save it. Run it. Now I have.
Your voice was breaking up. I don't know if anybody heard. I didn't hear.
Can you hear me better now?
Yeah, you started a little static, but it's clear again.
So you can. Yeah. Is it better now?
Yeah.
So what I was saying is, what I said last was, in conclusion, that would be a good conclusion, what you said. Given that the energy is 0.99%, I would conclude that my matrix, which was originally 6 by 5, can be compressed into a matrix of 6 by 2, and it retains 0.99% of the information. That's it. That's compression with singular value decomposition. Questions?
So I do have a question. So if you go back up to the original matrix, you said that like the algorithm, or it kind of split into two different groups, which is the first two columns, and then the last three columns, because how similar they are.
Yeah.
And I can understand that part, but the part that's kind of confusing me is that if we get rid of the last three columns, we still retain 99% of the data, but we don't, I mean, we do know the first two columns are similar, but we have no idea what the last three columns will even retain. So we can't even compare it because we don't really know what would be in it, if that makes sense. I don't know. Do you get what I'm asking?
Not really. You know, let me just remind you, these 5 columns are not the same as these 2 columns, right? You realize that, correct?
Correct.
Okay, so these are new. These are columns, like the example I gave of Thor. So if the first column is Thor, and the third one is Thor 2, and the fifth one is Thor 3, all that happened is that SVD created out of those 3 columns one single column called Thoriness. You know what I mean? You know, not for those 3 original ones, but level of Thoriness in the movies, something like that. And so basically what I said is, if you look, the first 2 are, you know, the first 3 are 5s and 4s, and the bottom ones are 0s and 1s, right? Whereas on this side, these 3 are 0s and 1s in the top 3s, and 5 and 4s in the bottoms. What I said is that it kind of picked up that, and that's why it needs to have 2 to kind of accomplish that difference. And that's where you get 99% of the energy. With just 1, it's kind of just picking up one of them and not the other one.
Oh, okay. I get what you're saying. Okay.
You know?
Yeah, kind of.
Kind of. What are you not on?
No, I mean, I'll just have to look at it more, but it's making more sense.
Your question, though, that was the problem.
What the question? I mean, you kind of explained the question, because the question was that, and I guess I was thinking they were the same data, just reorganized. But yeah, I get that the new splice data is a representation of the data combined, right?
The new slice data? What do you mean? These?
Yeah, that's a representation of all the data previously.
That SVD actually gave you this originally, right? So it gave you a 6x5 still, just like the original one, right?
Yeah.
It creates 6x5, or whatever it thinks it wants to create. It still creates a lot of columns. However, the beauty of this is that it gives you this, right? And it's telling you the importance of something, okay? Although these are exponentials, notice that this one is a -17 versus a 1, right? So that's a huge difference. And so what it's saying is, because we calculated the energy over here, it's saying, well, you can drop columns because they are in order, right? So it's telling you that the first column is more important than the next one, and the next one, and the next one, and the next one. And so what you do is you can, because you want to compress the data, you drop some of the columns that it created just to keep the most important ones. But remember, they're not the same. This is users to movies. Thor 1, Thor 2, Thor 3. There is no Thor 1, Thor 2 here. There might be not even Thoriness. It might be like guys that hit things with heavy hammers. You know what I mean? I don't know. But it picks up a new concept. And it's all done based on the statistics of the data. You see that?
Yeah.
Do you think that answers your question?
Yeah, no, I think you answered my question.
Hopefully I did. All right, guys, so that's basically compression and singular value decomposition. This concludes our discussion of this, okay? You know, the lecture, the theory of it. We are now ready to move on to a new topic, which will be reinforcement learning next Monday. However, I remind you, on Wednesday, we will do open lab, so everyone needs to come to class because I will be going over your homeworks, and then also the new homework assignments, recommender system. There's in the code, there's a few things that you guys need to take a look at that we will discuss on Wednesday. Make sense?
Makes sense.
Questions?
No questions.
So we'll stop here for today, and I'll see you guys on Wednesday, okay? Have a good day.